Welcome to the Water Environment Research Foundation's TERI tutorial series. This module will walk you through a case study for Plant A. This plant uses a 5-stage BNR-EBPR process to meet its total nitrogen and total phosphorus limits. Anaerobic digesters are used to stabilize the solids, and then centrifuges are used to dewater the sludge. The plant does experience nuisance struvite formation, which it manages by adding ferric chloride. The plant receives mostly domestic waste. It is designed to treat 24 million gallons per day, and the current average daily influent flow is 12 million gallons per day. The 5-stage modified Bardinfo BNR process is designed to meet the plant's effluent permit limits of less than 5 milligrams per liter of total nitrogen and less than 0.5 milligrams per liter of total phosphorus. This is the overall plant schematic for Plant A. Some highlights of the plant's process are as follows. Primary sludge and waste-activated sludge are thickened and then combined in the anaerobic digesters for stabilization. Supplemental carbon is added to the post-anoxic zone in the biological reactors to help drive full denitrification and meet the total nitrogen limits at the plant. Ferric chloride can be added downstream of the secondary clarifiers to improve the phosphorus removal in the downstream effluent filters. Ferric chloride can also be added to the sludge stream to reduce struvite formation in the digesters, centrifuges, and related pipes, as well as minimize phosphorus levels in the centrate recycle stream. Centrate recycle occasionally causes upsets in the enhanced biological phosphorus removal EBPR process. Some additional information that was entered for this case study includes the importance of each of the business case evaluation, or BCE, criteria, the average labor rate for operations and maintenance personnel at the plant, the feed rate and the cost for the supplemental carbon and the ferric chloride, and an estimate of the labor and the direct costs, including parts, materials, tools, spent dealing with the negative impacts of struvite forming in the system. Here is the summary of the influent, effluent, and side stream data that we have for Plant A. The additional nutrient data that is available for the side stream flows will make the estimates from TERI more accurate. If this data were not available, the tool would use default estimates for some of these values. When you first open TERI, remember to click Enable Macros when prompted. This allows the tool to operate correctly. On the Start screen, the plant data is entered, starting at the top of the green column and working down through each green box. When the question, "Are the side stream characteristics known?" is answered yes, the red box labeled "Click here to enter data for side stream" will appear. When the red box is clicked on, this screen, also known as the Type 1 input screen, appears. Again, data is entered in the green cells on the side stream characteristic input page. The data entered here comes from the plant performance data table that we looked at earlier. Enter all of the data that you have available. Leave the cells blank if you do not have that data. The tool will assume some default values for critical data if nothing is entered in those fields. The OK listed in the right-hand column indicates that the value entered is within the typical range of values for that parameter. While entering data, please keep in mind that the Clear Data button should only be used when you want to erase all inputs in a tab. To change individual entries, just click on the cell and use the backspace button to delete that particular cell entry before entering the correct value. The business case evaluation criteria weighting is entered as shown here. These criteria weights will determine the formula used to calculate the option score. Please note that for the 3 case studies shown in the TERI tutorials, all use the same criteria. This helps to make it possible to compare the results and to see how the different plant configurations affect the overall scores. The plant mass balance shows the concentration of solids and nutrients at various points in the process. The results for Plant A can be accessed by clicking on the Plant Mass Balance text at the top of the screen or by clicking on the MB Schematic tab at the bottom of the screen. Based on the data entered, TERI calculated these values for the mass balance before nutrient recovery for Plant A. The other boxes in the plant mass balance diagram are blank. Once all of the data is entered, the expected performance of several options and the capital and O&M estimate results can be viewed by clicking on the Capital and O&M estimate results at the top of the TERI screen, or by clicking on the blue tab labeled Results Struve at the bottom of the TERI screen. This is the screen with the results that will pop up. It presents a side-by-side comparison of the calculations for each of the following options: struvite crystallizer high estimate, struvite crystallizer low estimate, ferric chloride addition, and alum addition. The benchmark for the performance of these options is 85% removal of phosphorus, also referred to as P, from the side stream flow. Since there is 170 pounds per day of orthophosphorus in the centrate side stream, 85% removal would result in 144 pounds per day of phosphorus being removed. Please note that some nitrogen is also removed in a struvite recovery process. The chemical requirements section of the results page includes calculated amounts of various chemicals that will be required for each alternative to meet the 85% removal performance goal. The bottom portion of the results page presents a summary of the capital investment needed to install each system, the annual operations and maintenance costs to keep the system running, and the value of the struvite that will be recovered and the supplemental carbon that will not be needed once the side stream recycle P levels are reduced by 85%. Please note that since this plant is already using ferric chloride, no capital cost for installing this system will be needed. The business case evaluation, or the BCE, in the TERI is intended to help utilities take a very high-level conceptual look at struvite recovery for their facility. Capital and O&M cost estimates must be verified. Remember, all capital cost estimates are based on 2012 US dollars. The BCE rank scores are based upon the weights that were entered for the 13 specific business case model criteria. There may be additional criteria that should be used to assess the options. Therefore, the TERI provides a good starting point for looking at nutrient recovery options, but additional study and evaluation are needed before any fully informed decisions can be made on implementation. TERI uses several parameters in the financial portions of the BCE. The nominal discount rate is the assumed interest rate without inflation being taken into account. Therefore, the real discount rate is the interest rate adjusted for inflation. The evaluation period that the tool uses is 20 years. For Plant A, based upon the business case criteria weighting that was entered, the struvite recovery low estimate alternative has the best total score of 81.2. For comparison, the baseline scenario represents the conditions where the plant O&M staff take the necessary operational and/or maintenance steps to minimize the effects of nuisance struvite formation. This table shows how each of the BCE criteria areas contribute to the total score for each of the alternatives. This graph compares the net present cost for each of the 4 alternatives that are being evaluated. The lines for the alum and the ferric chloride show significant increases in the net present cost each year because the systems have significant annual O&M costs with no recovered product to sell or current chemical costs that can be avoided. The net present cost of the struvite low estimate alternative is slowly improving with time, which indicates that all ongoing O&M costs are covered by the value of the recovered products and the cost of the supplemental carbon feed that can be avoided once the struvite recovery system is put into operation. This last chart shows how the total scores of the alternatives for Plant A compare to one another. The struvite recovery options have significant environmental, health, social, and economic benefits over the ferric chloride or alum feed systems.